let me show you how the integral test can be used to approximate series. The result I'm referring to in the proof of the integral test, if you recall, we showed that under the assumptions that the integral test is valid, right? Under the assumptions that the function is positive, decreasing, and continuous, we had the following. Right, we proved this using Riemann sums. Now let's take an example. In one of the first exercises we did, we showed that the series 1 over n squared converges. We did that by applying the integral test. The integral test gave us convergence of this series, but it doesn't tell us what the series converges to. We don't know what the series converges to by just an application of the integral test. It tells us it converges, but now let's ask the question, what does it converge to? And the integral test will allow us to get an approximation of what that converges to in the following sense. We can, let's consider the following question. We showed that this converges. Let us approximate what this converges to. Let's approximate what the series converges to within 1 over 1,000. So what we're going to do is we're going to get a good approximation of what the series actually converges to. And how are we going to do that? You see, the sum from 1 to infinity of 1 over n squared you can add the first k terms. Right? If you add the first k terms using a calculator or computer, whatever, you're going to get an approximation. How good is that approximation? Well, it's exactly this, right? If you bring this to the other side, you get what your series converges to, which is this. We don't know what that is, but that's what it is. And if you subtract your approximation, what you get is the rest. But this, according to the proof in the integral test, this thing is less than or equal to the integral from k to infinity of 1 over x squared. And this is easily seen, I'll let you work that out, but that, let's work it out. It's the limit as n goes to infinity, the integral from k to n, 1 over x squared, which is negative 1 over x from k to n, which is 1 over k minus 1 over n. And as n goes to infinity, this goes to 0, so you get 1 over k. What are we saying? We're saying that the difference between these two things is less than or equal to 1 over k. So if you want the approximation to be to within 1 over 1,000, as long as this is less than 1 over 1,000, you're good to go. In other words, as long as k is bigger than or equal to 1,000, as long as k is bigger than or equal to 1,000, you're going to get an approximation to what the series converges to. That is to within 1 over 1,000. So what are we saying? If you add the first 1,000 terms using a computer, say, you're going to get some number. And that number is going to be an approximation to what the series converges to. How good of an approximation? To within 1 over 1,000. And there it is. So now we can use the integral test or the result in the proof of the integral test to help us approximate series. Now, I said we didn't know what the series converges to, right? The integral test gives us convergence of this series. It doesn't tell us what the series converges to. Now we're able to approximate. But it's a beautiful result that we actually know what the series converges to. It's a deep result. We don't have the machinery to prove it yet, but I can give you the result. This series actually converges to pi squared over 6. If you sum 1 plus 1/4 plus 1 over 9 plus 1 over 16 plus 1 over 25 and so on, the result is pi squared over 6. In fact, we also know 1 over n to the power 4. This converges to pi to the 4 over 90. And in fact, we have the result, or we can work out the result for all the even powers. But the p series, 1 over n cubed, which converges, right, because it's a p series where p is equal to 3, which is bigger than 1. This is a convergent series. Nobody knows what it actually converges to. This is still an open question. We know it converges by the integral test. We don't know what it converges to.